All right, so now we're going to discuss error analysis. And in particular, we're going to make sense of what we mean by saying that the Newton method converges faster than bisection, for example. Okay. All right, so to quantify that, we're going to introduce this notion of order convergence. Okay, so let's say you have a sequence of iterates. So this is a sequence which converges to alpha. And we define the error at the end iterate as the difference between alpha n and this limiting value alpha. Okay? All right. So if there exists positive constants m and p such that p is between 0 and infinity and m is between 0 and infinity, such that the limit as n goes to infinity of the difference between alpha n plus 1 and alpha is divided by alpha n minus alpha to the p power is equal. So this is obviously by definition equal to the limit as n tends to infinity of the error at the nth plus first stage divided by the error at the nth stage raised to the p power. And if that limit is equal to m, then we say that alpha n converges to alpha with order p. Okay. So I should say that what happens is that if you choose the wrong p, either m is going to be 0 or m is going to be infinite, right? And it's only sort of a distinguished value of p for which this limit is non-zero, but it's also finite. Okay. All right. So that's one thing. So let me sort of make a few remarks. So the first of which is that for large n, what this is basically saying is that the error at the nth plus first stage is something like m times the error at the nth stage raised to the p power. And the second thing is that if p is equal to 1, there's a stronger condition on m, right? You must have that m is actually between 0 and 1. Okay? All right. And that p equals to 1 corresponds to what we call linear convergence. Okay? So p equals to 1 as linear convergence. Okay. All right. So again, we want the limit as n goes to infinity of en plus 1 over en to the p power to be m, right? And then p is between 0 and infinity, and m is between 0 and infinity. All right, so that's sort of the essential point there. And so let's apply this to the bisection method and the Newton method. Okay? All right, so the first thing is bisection. Okay, so alpha n plus 1 minus alpha. So alpha n plus 1 minus alpha is less than equal to b minus a over 2 to the n plus 1. And then alpha n minus alpha is less than or equal to b minus a over 2 to the n. So the limit as n tends to infinity of alpha n plus 1 minus alpha over alpha n minus alpha is 1/2. Right, so the limit m is 1/2, and if you recall, specifically when p is equal to 1, which this is the case because the exponent in the denominators, or the denominator is only raised to the first power, so this is the p equals 1 case, right? The limit has to be between 0 and 1, which indeed it is, so this gives you what is called linear convergence. Okay, so p is equal to 1 here. All right. Okay, so let's look at the other case, which is Newton's method. Okay. All right, and so we want to establish a similar error result. Okay, so we have that alpha n plus 1 is equal to alpha n minus f at alpha n over f prime at alpha n. So I'm going to subtract from both sides alpha. So alpha n plus 1 minus alpha is equal to alpha n minus alpha minus f at alpha n divided by f prime at alpha n. All right, so I'm going to, if you recall, it's like when we derived this thing, we did a Taylor expansion about alpha n and evaluated that Taylor polynomial at alpha, right? Excuse me. So you have f at alpha, so that's 0 by definition, but that's f at alpha n plus f prime at alpha n, alpha minus alpha n, plus 1/2 f double prime at some unknown point c, alpha minus alpha n squared, right? So you have an equality because that actually is the Taylor remainder term. Okay, so with that, I can substitute it into this expression. So this gives me that alpha n plus 1 minus alpha is equal to alpha n minus alpha so I can right, so maybe I will sort of have an aside here, right? So 0 is equal to this. I have minus f alpha n over f prime alpha n is equal to alpha minus alpha n plus 1/2 f double prime at c, f prime alpha n, alpha minus alpha n squared. Okay, so this term here is this term. So you have an alpha n minus alpha plus alpha minus alpha n. Those cancel out. And you're just left with 1/2 f double prime at some unknown point c, f prime alpha n, alpha minus alpha n squared. Okay, so I can divide by alpha by the error, right? So the absolute value of alpha n plus 1 minus alpha divided by alpha n minus alpha squared. The square comes from this term here, right? I can look at the limit as n tends to infinity of this. It's going to be limit as n tends to infinity of 1/2 f double prime at c, f prime at alpha n. But you recall c is between alpha n and alpha, and you assume ahead of time that alpha n converges to alpha. So this is equal to 1/2 f double prime at alpha over f prime at alpha. Okay, and then we assumed, if you recall, that f prime at alpha is not 0, right? Okay, so that guarantees that the method is at least quadratically converging. Okay, All right, so that's basically just an example of how you might apply this definition of order convergence to the bisection method and to Newton's method. Okay, and we'll see this more as we keep going at this. All right, but again here, this is quadratic convergence. Which is p equals 2. Okay. All right, so that's the precise sense in which Newton's method converges faster than bisection. All right.